Let us now start the diagram of 8085 microprocessor. The diagram is divided into two parts with reference to this internal data bus. Since the 8085 microprocessor is a 8-bit microprocessor, the internal data bus is 8-bit. Whenever someone says that it's a 64-bit microprocessor, it means that the internal data bus is of 64-bit. It's a 16-bit microprocessor, meaning the internal data bus size is of 16-bit. Whatever this is the size of the bit size of the microprocessor is the bit size of the internal data bus, as well as of the most general purpose register also, and the general purpose registers also typically. So now this 8-bit internal data bus is dividing this diagram into two parts. In the above part are the two control, the serial controls and the interrupt control. The serial control has two pins, the SID and SOD, and the interrupt control has the interrupt pins, trap through INTR and the interrupt acknowledgement pin. Here, this is a temporary register which is a scratch pad memory for the microprocessor, where the microprocessor carries its rough work. It's not accessible by the user. It's not programmable. It will be used internally by the microprocessor. That is why it is also called as a scratch pad memory. What is a scratch pad? In simple terms, you have used slate when you were young or during your math practice. You write on it and you erase it with a duster or a rough cloth, and then again you write on it and erase with the duster. So same thing is this temporary register, which is used for internal calculations by the microprocessor. This is the accumulator. Now 8085 has total 7 registers, 7 general purpose registers. To make it more detailed, the 8085 has two types of registers: this general purpose registers and the special purpose registers. The general purpose registers are for general programming purpose, and the special purpose registers have special function assigned to them, associated with them. The general purpose registers are divided into two categories: the most general purpose register and the general purpose registers. 8085 has 7 general purpose registers. 8085 has 7 general purpose registers, of which the most general purpose register is the accumulator, and the rest of the 6 are the general purpose registers. All the general purpose registers, the 7 general purpose registers in the 8085, are 8-bit registers. The first general purpose register, which is also the most general purpose register, is called as the accumulator. This is the default register of 8085. Now this is the ALU, the arithmetic and logic unit, which we have done in we have studied the circuit diagram and everything in the class lectures for ALU. This is the arithmetic and logic unit, which performs the arithmetic and logical operations. All the arithmetic and logical operations in the microprocessor are performed in this unit. This ALU is associated with flags. So whatever instruction is carried out, if it's an arithmetic instruction or a logical instruction, then its the values of the operations will always also be reflected in the flags. In the flags, it's a 8-bit register, but 3 bits are ignored and only 5 bits are used. We've studied that there are 5 bits in the flags called as the carry, the auxiliary carry, the sign, the 0, and the parity. We have studied their functioning. Or for the sections B and C, we will study their functioning a little later. Okay. Now the instruction register. The instruction register is the register where the instructions are brought while executing a program. Whatever instruction is now being executed by the microprocessor will be brought into the instruction register. It's an 8-bit register, and from this instruction register it will go into an instruction decoder, which will decode the instruction, and then a machine cycle will be executed for the execution of this particular instruction, which has just been brought by the microprocessor. So machine cycles are executed for this, and when all the machine cycles finishes, that means this instruction has been executed. Now another instruction is required to be brought in. So these are the general purpose register. We'll ignore the XZ. We'll start from the BC, the base, the count, the data, the extra DE, the HL, the high and the low. Individually they are all 8-bit registers, but these general purpose registers can also be used in pair form. B can be paired with C, D can be paired with E, H can be paired with L. BC will make a 16-bit register. DE will make a 16-bit register. HL will make a 16-bit register. But B can never be combined with E, D can never be combined with C. B will be combined only with C, and of which upper byte will always be B and the lower byte will always be C. The upper byte will always be D of the DE pair, and E will be the lower byte. The H will always be the upper byte and the L will be the lower byte. This is the rule and it cannot be overridden. Okay. Now we know that the registers in 8085 are divided into two categories, the general purpose registers and the special purpose registers. Having done the general purpose registers, let's move on to special purpose registers. There are three special purpose registers: PC, the program counter; SP, the stack pointer; and incrementer and decrementer. PC, program counter, holds the address of the next instruction to be executed by the CPU. Meaning if my program is being executed and the microprocessor is executing instruction number 10. So instruction number 10 will be brought into instruction register. At that time, PC will be storing the next instruction. That is, maybe PC will be storing 11, because what instruction has just been fetched into the instruction register? Instruction that was on location number 10. So now PC will be holding the value of the next instruction to be fetched by the microprocessor. That would be 11. Okay, we'll study this in detail. Stack pointer points to the top of the stack. Incrementer, decrementer is a special purpose register which is used to increment or decrement the contents of PC and SP. So it's also a 16-bit register pair. Okay, now this is the timing and control. We have studied all the pins in this timing and control: X1, GND, VCC, X1, X2, clock out, DMA, hold and HLDA bar pins, RD bar, WR bar, IOM bar, S1, S0, reset in bar, reset out, ALE. And we've also studied AD7, the A15 to A8, and AD7, AD0 at the address bus and the address data bus. So this brings us to the end of 8085 microprocessor. Now we will be taking up the PC and SP in our in the lecture. So now let us understand what PC is. Program counter. PC is program counter. So now let us suppose that our program is like input A, input B, C equals to A plus B, output C, and end. Okay. So now for it is written on 10, 11, 12, 13 and 14. So now the start address of this program is 10. Okay, the start address is 10. So now start address is loaded into PC. So now microprocessor does not know from where it has to start executing. It will always, whenever it has to execute a program, it will check the contents of the program counter. So now the start address of this program is required to be executed, and the start address of this program is loaded onto 10. So the microprocessor has finished off its previous execution and now it is moving on to the next execution. So first thing that it would do is it's directionless. So for directions, it will contact PC. It will check the value of the PC. PC, the program counter. PC is holding 10. The microprocessor immediately goes onto the location number 10. What is written on it? Input A. So it will execute input A. But when the instruction on location number 10 is being fetched at that time the value of the PC, at the same time the value of the PC will be incremented by 1 and it will now store 11. So when once the execution of instruction written on 10, line number 10 has finished, the microprocessor will again go back to PC, checking its content so that it knows where it has to go, which instruction has to execute next. So what does it get here? It gets a 11 here, so it will go to 11. This is how the next instruction is fetched. As soon as simultaneously when it is fetched, the value is changed to +1, 12. So now it has executed this, it will go back to PC which has 12 here, so it will fetch the instruction written on 12 and simultaneously the value of PC will be incremented by 1. Now PC is storing 13. After this, when the CPU has executed the instruction written on 12, it will come back to PC asking where it has to go now. So the PC will tell it that you have to go to 13. So it goes to 13 and it fetches output C into the instruction register that we've just studied in our block diagram. And so as soon as this is fetched into the instruction register, the content of PC are incremented by 1. So now output C is executed. After finishing of this execution, the microprocessor comes back to PC. Where I have to go now? The PC tells it 14. It comes to 14. It fetches the instruction written on 14 and increments the value of PC. But when once executing the instruction on 14, it comes to know that it has reached the physical end of the program. So now it will not go to the PC for this program. It knows now that the instruction has finished for this particular program. Now it will go for another program. Okay. Now this is a sequential program. Now let us take an example of a modular program where there is a sub program in the main program. So let's take an example. 10 again, start address is 10. Input A. 11 has input B. 12 has call XYZ. XYZ is address 24. Okay, so 24. Okay, 13 is D equals to C into 2, and 14 is end. No, 14 is output D and 15 is end. Okay, now XYZ here, this is a subprogram and it has gone out of focus, right? Let's take it a little close. So 24 has the XYZ function written subprogram. So 24 has call XYZ. So XYZ is written here, which is C equals to A plus B, and on 25 it is written print C or output C, and 26 it is written return. So how this program is executed: when start address is encountered, PC is loaded with 10. So now the microprocessor comes to PC. It knows that it has to start the execution of a program. The program has been loaded. Now instructions are coming into it. Now how instructions will come into it? The CPU will ask PC, where do I need to go? It checks the contents of PC, and the PC is holding 10, so it will go onto line number 10 and will fetch instruction written on line number 10. As soon as it fetches the instruction in instruction register, this is incremented by 1. So now this is executed. So after execution, the CPU comes back to PC. What is written here? 11. It will go to 11. It will fetch the contents here, and simultaneously when it is fetching, the contents of PC are also incremented by 1. It becomes 12 now. So now input B is executed. Now it goes to PC. PC tells it 12. So it goes to 12 and fetches the instruction written on line number 12. When it is fetching, that time it is incremented by 1. It becomes 13 now. But call XYZ is written on 12. It was fetching, when it was fetching the instruction written on line number 12, the value of PC was incremented by 1. But when this instruction is executed, this is a call instruction. A call instruction syntax is that whatever is the address of this subprogram is required to be written on PC. So now 24 is required to be written on PC, which is holding 13. Okay, you cannot lose this value. So what happens when call is executed? The value of the PC is written on the stack pointer. Top of the stack, 13 is written here. Okay, so now let me take it in a little focus onto the stack. Stack pointer is pointing here, 13 will be written here. So now our value is safe and 24 is written here. So now after executing this instruction written on line number 12, the CPU goes to check the value of the PC. PC is now holding 24. So where will the CPU now go? It will go here. What is written here? C equals to A plus B. So it will execute C equals to A plus B. Whatever is the value of A and B will be added and it will be stored onto C. When it is fetching the instruction written on line number 24, the value of PC would be made 25. So now after executing 24, the CPU goes to PC. What is written here? 25. When 25 is written here, it fetches the instruction written on line number 25. When it is fetching, the value is made of PC is made at 26. After finishing the instruction written on executing the instruction on line number 25, it goes back to PC. Where do I need to go now? The PC says you need to go to 26. It goes to 26. It fetches 26 and simultaneously the value of the PC is incremented. But when this instruction is executed, this is a return instruction. This instruction says that now put the what does a return instruction say? Put the value of the stack pointer back to the PC. So this will be cut and PC will now store 13. So after executing this instruction, the CPU goes back to PC. PC is storing what now? 13, because the return made sure of it that the value which was stored onto stack pointer is brought back to and written back to the PC. So now when CPU comes back after executing return instruction, what value does it get on PC? It gets 13. It went from here to here. Okay, it went from here to here and it has now come back here. So it went from X, it is coming on X plus 1. Now the execution resumes. This is how subprograms are executed, and so we have studied how PC, SP and incrementer-decrementer work. Incrementer and decrementer are used to increment and decrement the values here. So it's very clear. We have studied what is the function of PC program counter, SP stack pointer. Stack pointer holds the value of the PC whenever a call, return instruction is executed or some other instructions. Okay, thank you.